Dear ladies and gentlemen, dear colleagues, I am glad to present to your attention a paper with the following subject: development of automotive quality high-strength steel microalloying principles to reduce production costs with keeping required mechanical performance. In recent decades, one of the main directions in the development of steels for automobile body sheet has been increased in strength. This makes it possible to reduce the weight of vehicle, meet legal safety requirements, reduce fuel consumption and other energy resources, improve the environmental situation. Hot-rolled, low-alloyed, high-strength steels for automobile body sheet with a yield strength from 315 to 420 megapascals are currently widely used. The peculiarity of current trends in the production of these steels in the world is to reduce the cost due to the complete or partial replacement of niobium with titanium. At the same time, the patterns of influence of the chemical composition and thermal deformation treatment in the metal on the resulting structural state are mechanical properties of hot-rolled steels, which makes it possible to develop the most economical automobile body sheets have not been fully studied. To achieve this goal, appropriate scientific researches are needed. This report presents the results of work being carried out in this direction. The studies were carried out on samples of hot-rolled steel from 3 heats with the same carbon content and different titanium content. The main components of the chemical composition and the main parameters of hot rolling are presented in the tables on the slide. Steel of the first composition was cast into melt of niobium microalloyed steel. The first batch had a transitional composition and contained niobium. Transitional steel is steel number 2. Excuse me. The methods of optical and electron microscopy were used in the work. Metallographic examination showed that the rolled products under study have high metallurgical quality, rare sulfide inclusions, single sparse oxide lines, point inclusions such as point oxides, and rare inclusions of nitrites in the form of separate precipitates were identified. No coarse, non-metallic inclusions were found. Particular attention has been attracted to sulfide inclusions in steels number 1 and 3 that have been microalloyed with the titanium. In these rolled steels, along with thread-like precipitates of manganese sulfide, there are globular precipitates with the contained titanium. As a rule, presence of stitch of line or line inclusions leads to a decrease in ductility and thickness. Complex titanium-containing sulfides are harder and less deformable. Therefore, they don't have such a negative impact on their properties. This slide shows images of microstructure obtained on the surface and the axial zone of rolled samples. All produced hot-rolled samples had a ferrite perlite structure. It can be seen that the microstructure is finely dispersed and fairly homogeneous without any grain variations across the cross-section of the rolled products. Only for rolled products number 2, with niobium, there is slight heterogeneity and a difference in grain size. This is due to the fact that for steels microalloyed with titanium, the use of high temperature or the end of rolling in the roughing group or of stands contributes to obtain a homogeneous microstructure. The occurrence of chemical heterogeneity and difference in grade size across the cross-section is associated with redistribution of carbon caused by formation or carbides or microalloying elements. The figure shows uh, the results of thermodynamic calculation of stability conditions for all possible phase precipitations in the steel number 1 and 3. It can be seen that according to the calculation, the precipitation of titanium carbide begins at 1100 degrees Celsius. However, in austenite, this process is kinetically 100. Therefore, its intensive precipitation and accordingly the element of surface layers of rolled product with carbon will occur at temperatures significantly below the 1000 degrees Celsius. The results of assessing the grain size showed that for steel number 1 and 2, the average grain size was from 5.3 to 5.8 microns. For steels number 3 and 4, the range of values, including all batches of rolled products, was 4 times larger, from 4 to 6 microns. This is due to the wider range of coiling temperature used. The figure shows the dependence of the average grain size of rolled steel number 3 on the coiling temperature. It can be seen that the higher the coiling temperature, the larger the grain. However, the results of grain size assessment and the previous figure indicate that the macrostructure of studied hot rolled bench is quite fine. The next two present the results of mechanical tests of rolled samples of various batches in the form of diagrams reflecting the range of obtained values. The red horizontal lines indicate the minimum level of properties that meets the requirements of the European standard. It can be seen that roll seats number 1 and 2 correspond to the S420 MC grade and steel number 3 to the S355 MC grade. Steel number 4 does not correspond to the S355 MC grade. This may be due to both difference in chemical composition and the structural state which is influenced by the parameters of thermal deformation treatment. This slide shows the dependence of the yield strength and tensile strength on the temperature of the hot rolling and for steel number 1 and 3, which have different titanium content. It can be seen that with increasing this temperature, the strength characteristics for both steels increase. This slide shows the dependence of the yield strength and tensile strength of the coiling temperature for the same steel number 1 and 3. It can be seen that opposite dependencies are observed. This is likely due differences in the temperature range used. For rolled steel number 3, the coiling temperature are higher. They reach approximately 600 degrees Celsius and higher. To explain the results obtained, a more detailed study of the structural state of the studied rolled steel was carried out. Samples of rolled steel number 1 and 3 from batches with maximum and minimum strength were studied by transmission electron microscopy. The result obtained indicates that the macrostructure of rolled samples of both steels contained polygonal ferrite with a descalation density from low to moderate. The type of cementites containing areas varies from perlite to degenerate perlite with variations in between. For example, in the right figure, you can see that the right part of the cementite containing area is perlite, while the central and left parts contain degenerate perlite. In all samples of the rolled products under study, submicron precipitates of titanium nitride and carbonitride were detected. The shape of the precipitates in the images varies from square or rectangular to round. Typical precipitates size range from 0.2 to 0.5 of a micron. Some precipitates range in size from 1/10 to 1.5 microns. Analysis of interplanar spacing showed that these precipitates have the titanium carbonitride composition with various fraction of carbon. Nano-sized precipitates of titanium carbide in these studied samples differ both in volume, fraction, and in the type. Austenitic precipitates are formed during hot deformation in austenite. Interface precipitates are formed during the transformation of austenite into ferrite. There are ergen in layers at regular intervals. Precipitates from in ferrite were not found in any of the samples. There are a few austenitic precipitates in all samples. The typical size in rolled steel number 1 is from 5 to 15 nanometers. They are round up to 20 nanometers. In samples of rolled steel number 3, the size of these precipitates is from 5 to 12 nanometers. In all samples, precipitates of the interface type predominate. In rolled samples of the both steels with the minimum strength, the diameter of the precipitates is most area averages from 4 to 8 nanometers. Up to 15 nanometers are found also in steel number 1 with maximum strength. Our precipitates are smaller. Their diameter is approximately from 3 to 6 nanometers. Up to 10 nanometers are found also. The smallest precipitates were found in samples of rolled steel number 3 with maximum strength less than 2 nanometers. The size of large ones didn't exceed 4 nanometers. Analysis of the presented results shows that the formation of interface carbide precipitates had been greatest effect on increasing strength. Their influence depends on their number and size. The finer the precipitates, the higher the contribution of dispersion hardening. At the same time, the plasticity is also high. The samples with a low strength, the precipitates, were on average larger. In the samples with the maximum values of the yield strength and tensile strength, The smallest precipitates were found 2 nanometers or less. The amount of precipitates preliminarily depends on the titanium content. Therefore, the strength of steel number 1 is higher than the steel number 3, and the steel number 4, which doesn't contain titanium, has the low strength. On the other hand, the amount of precipitates and their size depend on the hot rolling and coiling temperature. The influence of hot rolling and coiling temperatures is due to the following circumstances. Higher temperatures at the rolling and contribute to the preservation of large quantities of fast-forming components in the solid solution. Therefore, during cooling and coiling intensive formation of a large number of new nano-sized precipitates occurs, and as a result, the contribution of dispersion hardness increase. At higher coiling temperature, the components retain a very high diffusion mobility, and consequently, the formation of precipitates occur more intensity. However, in an increase in the cooling temperature above 600 degrees Celsius leads to a noticeable increase in grain size and precipitates, and accordingly a decrease in grain boundary, strengthening dispersion hardening and strain characteristics. Using only titanium microalloying, it is possible to produce economical high-strength hot-rolled steels for automobile sheet for strength classes 355 and for 120 megapascals in accordance with the requirements of the European standard. One of the positive factors is the presence of inclusions of complex sulfides of global shape contains titanium, which have a beneficial effect on mechanical properties of studied rolled steels. The justified use of elevated temperature at the end of rolling in the roughing group of stands and coiling promotes both the formation of a finally dispersed and uniform microstructure of the titanium microalloyed steel under consideration, and the achievement of a high level of strength and ductility due to dispersion hardening during the implementation of the interface precipitation mechanism. The possibility of continuous casting of the development higher strength titanium microalloyed steels onto niobium microalloyed steel has been established. Thank you for your attention.